Hi everyone, this is Tim with a brief announcement before we get to our pre-lab lecture for experiments 4 and 5 this year. When we were looking at the schedule of the lecture versus the schedule of the experiments, we realized that it would be in your best interest, in order to have as much time to learn stoichiometry before you did the experiment on that. So what we've decided to do is we've decided to move the stoichiometry paper experiment to be experiment 5, and the empirical formula experiment of copper sulfate to be experiment 4. Unfortunately, we already printed the lab manuals, so we can't reflect that change in the lab manuals because there's simply too many of them ordered in order to reorder all of them. But we have changed it on the syllabus, which you can find on Blackboard, and the experiment schedule also found on Blackboard. So please make sure you're following the experiment schedule and syllabus on Blackboard, not the lab manual, because we're going to do experiment on finding empirical formula as experiment 4, and we're going to do the stoichiometry paper lab as experiment 5.
Hi everyone. So in this video, Tim and I are going to go over the stoichiometry paper lab, and Tim will do the pre-lab with you in just a few minutes if you want to stick around for that. So basically, what I want to do before I go over some introduction to stoichiometry is I want to let you know that in the description of this video, you can find what I would kind of call a mini course about stoichiometry, and it starts with grams to moles and then talks about solid state stoichiometry and then limiting reagent and theoretical yield, and then it talks about molarity and solution stoichiometry, and it's actually 5 different videos. In total, it's probably somewhere around an hour and 30 minutes of video. It would help you out tremendously if you're not sure how to do these things, to watch those videos and to take notes. Stoichiometry comes up over and over and over again in chemistry, even in organic chemistry, especially in the lab. You're doing stoichiometry. In Gen Chem 2, you're doing stoichiometry, and throughout this course. Said another way, the sooner you master this, the more points you're going to get, because you're going to get points for this throughout your chemistry career. So it's really important to master this topic. With a little bit of hard work to get down the basics and then some practice, you can really master this and make sure that you earn all of those points. So I'm going to, in this video, very briefly go over some of the key points that are illustrated in the 5-part video series, the mini course below, but I don't want to you to think that this is everything, or that this is enough detail or anything like that. This is just meant for as a refresher, mainly for people who are pretty close to already knowing how to do the stoichiometry. It's just a brief refresher. So the first thing that I think is really important is, well, why the heck do we want to know stoichiometry in the first place? Okay, and I think that this is sometimes an overlooked aspect of stoichiometry, and students just see it as, hey, you got to do a bunch of math. But instead of thinking about it as a bunch of math, we might want to think about, why does someone care? So I have an example here of a reaction that you're actually going to perform in the Gen Chem lab later in the semester. And essentially what we have here is something called salicylic acid. Salicylic acid is a compound found in like facial cleansers or acne medication. So this is salicylic acid. This has very similar pain relieving properties of what we're going to turn it into over here. This is called aspirin. However, it's too acidic, so you can't really eat it. By adding what is called acetic anhydride, we can weaken the acidity of this molecule and turn it from something that we can't eat into something that we can eat and have pain relieving properties. Well, what does that have to do with stoichiometry? Well, so far nothing. But what it has to do with stoichiometry is, let's say I work for Bayer Aspirin Company, okay? And I am the person who orders the salicylic acid and the acetic anhydride in order to make the aspirin. Well, if I know how much aspirin is in each tablet, and I know how many tablets I need to make every day or every week or whatever it is, I can know the mass of aspirin that I must synthesize. What stoichiometry allows us to do is, it allows us to calculate how much salicylic acid and how much acetic anhydride are required to make that much aspirin. That is a very useful thing. We're not just guessing. If we mix these two things together, we'll get some amount of this stuff, and we never know how much we're going to be able to make. We can actually calculate it out. So stoichiometry allows us to, using masses of starting materials, predict how much product we can make. or using a mass of product, predict how much starting materials we would need. So this is basically what stoichiometry is useful for. And what we want to do now is, or I want to do now, is go through several examples of how we're going to kind of build up step by step how we can do these stoichiometry problems. So the first thing we need to be able to do in stoichiometry is be able to convert from grams to moles. So I'm going to take an example where I have 15.2 grams of water, and I want to know how many moles of water I can make. And to do this, we're going to use a process called dimensional analysis. And in dimensional analysis, we need an equality between grams of water and moles of water. And that's where the periodic table comes in. So water is made up of two hydrogens, H2, and an oxygen, O. So if I want to know how many grams of water in a mole or in a mole of water, I want to use a periodic table. And specifically, it's 2 times 1.01, because there's two hydrogens, plus 16.00, the mass of oxygen. So in order to find the molar mass of water, I want 2 times 1.01 grams, the mass of hydrogen, because there's two of them, plus 16.00 grams, the mass of oxygen, and there's only one. And when I do that math, I get 18.02 grams for the molar mass of water. Now we can write this as an equality. And that equality is that 18.02 grams of water equals 1 mole of water. So every mole has a mass of 18.02 grams, or every 18.02 grams is 1 mole. Now if I want to convert from grams to moles, I start with 15.2 grams of water times, I want to put one thing of my equality on the bottom and one thing of my equality on the top. So if I want grams of water to cancel out, I'm going to put the unit with grams of water on the bottom. So I'm going to put the 18.02 grams of water on the bottom, and on top, I'm going to put 1 mole of water. To do the math, I multiply by the top and divide by the bottom. And when I do that, and I round to 3 sig figs, I get 0.844 moles of water. Now, if you're not familiar with how to do this, I would again suggest the videos below, but I would also suggest that you take notes as you watch this video. Most people learn things faster if they write it down. So everybody likes to learn things faster, so writing it down can be a good strategy. Now, if we wanted to do this the opposite way, and let's say that we start with 0.844 moles of water, and we want to know how many grams of water that is. Well, this is a pretty easy question because we just found that it's 15.2 grams of water. But how would we do this mathematically? It turns out we use the exact same equality. We're not going to use a different equality to do this. We're just going to use the equality in a different way. So if we want to convert from grams to moles or moles to grams, we always use molar masses. So in this case, we have 0.844 moles of water times. Now I want moles of water on the bottom, so moles of water will cancel out. So I put 1 mole of water on the bottom. And on top, I put 18.02 grams of water. So I will get rid of my moles and end up with grams. And when I do this, not surprisingly, I get 15.2 grams of water. So 15.2 grams of water is 0.844 moles of water, and 0.844 moles of water is 15.2 grams of water. These two things are the same amount of water, they're just in different units. So we have to be able to convert from grams to moles and moles to grams. In order to do that, we always use a molar mass, or said another way, a periodic table, which is where molar masses come from. Now, to be honest with you, in the lab, if you're using larger substances, okay, things more complicated than water, say C3H8, which is propane, you might look it up on Google, okay, if you want to get the molar mass instead of adding it up on a periodic table. Now let's look at another example. All right, so moving right along here, and we're moving relatively quickly from what is a couple weeks worth of lecture in a few minutes, but again, there are videos down below. Here we have a balanced chemical equation, which again involves our water. And it says 2 hydrogen gas plus oxygen gas yields 2 water gas. And you'll notice we have 2 times 2, which is 4 hydrogens on this side, and 2 times 2, which is 4 hydrogens on this side. And we have 2 oxygens on this side, and 2 times the 1 oxygen in water on this side. So we have the same number of hydrogens and oxygens on both sides. So this is a balanced chemical equation. It's really important that in chemistry, we are going to use balanced chemical equations, and we're not going to make atoms appear or disappear. Okay, it's not magic. Even though we can't see it happening, it's still not magic. Well, we can make equalities out of this. And balanced chemical equations allow us to convert from moles of one thing to moles of another. So for example, if I did a reaction here with 2 moles of hydrogen, I would find that that is exactly equal to 2 moles of water. Because the balanced chemical equation says for every 2 moles of hydrogen, I will yield 2 moles of water. Well, if I wanted to use 1 mole of oxygen, which is the stoichiometric coefficient in front of oxygen, I would yield 2 moles of water. So 1 mole of oxygen, there's no number here, so it's a 1, yields 2 moles of water. And you can also do this backwards. I can actually do this what's a little bit backwards. I could figure out if I had hydrogen and I wanted to react it with oxygen, what is that equality? Well, this equation says that 2 moles of hydrogen requires 1 mole of oxygen to react. So in the first example, we learned how to convert from grams to moles and moles to grams. In the second example, we learned how to use a balanced chemical equation to look at the relationships between moles of one thing and moles of another. We could use these equalities to do dimensional analysis. So now we can put these 2 concepts together and answer this last question, which says if 18.6 grams of oxygen is reacted with excess hydrogen, how many grams of water will be produced? What we'll notice here is that in the balanced chemical equation, the units that are related are moles and not grams. So we can't consider the grams of oxygen. We need to take the grams of oxygen and convert it first to moles of oxygen. Once we have moles of oxygen, we can figure out how many moles of water will be produced. Because we can convert from moles of oxygen to moles of water using what? A balanced chemical equation. So we can convert this to moles of water. Then finally, it doesn't ask us how many moles of water are produced. It asks us how many grams of water are produced. So we can convert from moles of water to grams of water using the molar mass. So there is no direct way, one-step conversion, to convert from grams of oxygen to grams of water. We need this 4-step process where we go from grams to moles to moles, and moles to grams. Because we always need a direct relationship between the units. Balanced chemical equation gives us a direct relationship between one compound and another, in this case oxygen and water, but the units have to be moles. So let's start this problem. If we start with 18.6 grams of oxygen times, well, we use our periodic table and we know that oxygen is O2, so there's 2 of them. So 2 times 16 is 32 grams of oxygen, and I want grams on the bottom so it'll cancel out. And 32 grams of oxygen is exactly equal to 1 mole of oxygen. Times. Now I want to convert from moles of oxygen to moles of water. Whenever you want to convert from moles of one thing to moles of another, you need to use a balanced chemical equation. So in this case, I want moles of oxygen on the bottom so it'll cancel out. If I look at my balanced chemical equation, there is 1 mole of oxygen. On top, I want moles of water. If I look at my balanced chemical equation, there are 2 moles of water on top. You'll note that this is the same as this middle equality that we wrote. 1 mole of oxygen, 2 moles of water. In dimensional analysis, all of these conversion factors, these fractions if you will, come from equalities. Now I want to convert from moles of water to grams of water. Now you may remember from the previous question, we know that 1 mole of water is 18.02 grams of water, which we found by adding our 2 hydrogens and our oxygen on our periodic table. Well, what do we want on the bottom? We want moles of water to cancel out, so we put 1 mole of water on the bottom, and we put the 18.02 grams of water on the top. Now to solve this mathematically, we multiply by the top, divide by the bottom, multiply by the top, divide by the bottom, repeat until you get to the end. Note that if a number is 1, you don't actually need to type it into your calculator because anything times 1 is the same number. When we do all of that math and we round to 3 significant figures, we find that reacting 18.6 grams of oxygen will yield 20.9 grams of water. So in these 3 questions, we kind of built up how to do what I call solid stoichiometry. So basically, we did grams to moles, we looked at how that interacts with a balanced chemical equation, and then we converted from grams of one thing to grams of another thing. There's another type of stoichiometry that's important, and that type of stoichiometry is called solution stoichiometry. And in solution stoichiometry, we need to basically use concentrations of solutions. And the specific concentration of a solution that we use is something called the molarity. And molarity is abbreviated big M. And this is a quantitative unit for concentration as opposed to a qualitative things like concentrated and dilute. But this is moles of solute, the thing that is dissolved, divided by liters of solution. So if we were to make, for example, a salt water solution, the salt would be the solute. So it would be the moles of the salt divided by the total volume of the solution. And if you'll notice, because this unit has moles in it, it's another way to find moles. You can convert from grams to moles using a molar mass, as we just did several times in previous examples, but you can also convert from liters to moles using a molarity, which is the only other thing you really need to know how to convert to moles until you get much later in this course. So let's take an example of this. An example is that a student makes 250 milliliters of a solution with 4.91 grams of NaCl. What is the molarity of the solution? So in order to do this, I'm going to do it in something that looks like dimensional analysis. Do you have to do it this way? No. You could find moles, you could find liters, and you could plug in. But I'm going to do it in something that looks like dimensional analysis. So I'm going to convert from grams of NaCl to moles of NaCl, and then I'm going to divide the moles of NaCl by the liters of the solution. And moles divided by liters gives me molarity. Note that this last step is not truly dimensional analysis because I'm changing units. I'm not finding an equality. So it looks like it, but it's not technically dimensional analysis. So if we start here with 4.91 grams of NaCl times, I want to put the convert the grams to moles. Well, what do I use to convert to grams to moles? I use a molar mass. Na is 22.99 and Cl is 35.45. When I add those together, I get 58.44 grams. I want grams on the bottom, so it'll cancel out. So I put the 58.44 grams of NaCl on the bottom. Well, how much NaCl is this? This is 1 mole of NaCl times. Now, the next step looks like dimensional analysis, but technically isn't. I'm going to put a unitless 1 on the top. Why do I do that? That will simply bring the moles over. So the moles just go over here. So grams canceled out and I have moles. If I put a unitless 1 here, moles come over. Now I want to divide by the volume of the solution in liters. we need to be aware that 1 liter equals 1,000 milliliters. Solution volumes are often in milliliters, and 1 liter equals 1,000 milliliters. Said another way, we want to divide this by 1,000. And when we do that, we get 0.2500 liters. Now that'll bring the moles over, and I'll get moles over liters, which is molarity. And when I do that, I take 4.91 times 1, divide by 58.44 times 1, divide by 0.250. And when I do that, I get 0.336 molar NaCl. So molarity is another unit, which includes moles, which is very useful in stoichiometry problems. Now, let's look at another example where we're going to find grams from the molarity. It says a student has 250 milliliters of a 0.336 molar NaCl solution. How many grams of NaCl are in the solution? Now, if we look at this, we know the answer. You may not be aware of this, but it's actually the same question as above. So we have 4.91 grams gives us 250 milliliters of a 0.336 molar NaCl solution. But now we essentially want to do this question backwards. So Tim just pointed out to me that there's a typo here, and this should be 336 molar NaCl solution. So a student has 250 milliliters of a 0.336 molar NaCl solution. How many grams of NaCl are in the solution? So basically, we got 0.336 molar when we use 4.91 grams. So when we do this, it should give us 4.91 grams. But the point here is we're just asked the same question backwards. And the idea that I want to show you is that when we're asked the same question backwards, we don't just exactly do the math backwards. I mean, ultimately that's what we do, but it's important to think our way through it. Whenever you're asked for the mass of something in a specific solution, what you want to do is you want to convert from liters of, in this case, the NaCl solution to moles of NaCl. Because as we learned previously, once we have moles, we can find masses. Okay? And as you're going to see in the next problem, once we have moles, we can also do stoichiometry. So in the previous examples, we needed to convert from grams to moles. In the molarity question, we need to convert from liters to moles. So there's only two things you need to convert to moles: grams, molar masses, or liters, molarities, to moles. Then we can finally convert from grams of NaCl. So the first thing we need to be aware of is that we need to always use liters. We can't use milliliters. So we need to divide that by 1,000. So we want to start with 0.2500 liters of NaCl times. All right. Now we want to convert from liters to moles. How are we going to do that? Well, we know that this is a 0.336 mole per liter solution. And what we need to realize is that this should be moles per liter. So what we need to realize is that if this solution contains 0.336 moles of NaCl for every 1 liter of solution. So we want to put 1 liter of the NaCl solution on the bottom. How many moles does it contain? It contains 0.336 moles of NaCl. So when something is 0.336 molar, it's 0.336 moles per 1 liter. We want liters to cancel out, so we put the 1 liter on the bottom. Now we want to convert it to grams. Well, we want to get rid of moles, so we put 1 mole of NaCl on the bottom, and we'd already figured out the molar mass. We put the 58.44 grams of NaCl on the top. And when you do this math, you get 4.91 grams of NaCl. Not surprisingly, because we just did it backwards. Notice that these don't look exactly the same as just doing this backwards. So it's important to think your way through it, because they are doing it backwards, but we do need to show that it's a slightly different process. This takes practice. In my experience of teaching general chemistry for 10 years, this is something that students struggle with the most, converting from liters to moles and doing solution stoichiometry. Unfortunately, the best thing I could tell you is, if you want to get good at it, keep practicing, okay? Practice makes perfect, like anything. All right, so it says how many grams of AgCl can be formed from reacting 27.2 milliliters of 0.336 molar NaCl with excess AgNO3. So we again have our 0.336 molar NaCl solution. So here we're given a balanced chemical equation for the double displacement reaction between AgNO3 and NaCl, and we form insoluble AgCl, which precipitates out. And we're asked for how much of it we can form. Well, in this case, we need to find moles of NaCl that we have present. Then we can use the balanced chemical equation to find moles of AgCl, and then we can use the molar mass of AgCl to find the grams of AgCl. So, in this case, we want to start with liters of NaCl solution. We then want to convert that to moles of NaCl. Don't forget, whenever you want to convert from liters to moles, you need a molarity. Whenever you want to convert from grams to moles, you need a molar mass. Now we want to go from moles of NaCl to moles of AgCl. And what's important to note here is, when we're converting from moles of one thing to moles of another, we use a balanced chemical equation. It makes no difference that we found these moles from liters or we find them from grams. Whenever you go from moles of one thing to moles of another, balanced chemical equation. Then finally, we want to go to grams of AgCl, moles to grams, molar mass. Liters to moles molarity, moles to moles balanced chemical equation, moles to grams, molar mass. So let's set this up. First things first, we cannot use milliliters, so we have to divide this by 1,000. So we want to start with 0.0272 liters of this NaCl solution. We want to convert it to moles. What this 0.336 molar tells us is that for every 1 liter of this NaCl solution, we have 0.336 moles. Since we want liters to cancel out, we put 1 liter of NaCl on the bottom, and the 0.336 moles of NaCl on the top. Now we want to convert from moles of NaCl to moles of AgCl. Balanced chemical equation. We have 1 mole of NaCl. We want moles of NaCl to cancel out, so we put the 1 mole of NaCl on the bottom. And we have 1 mole of AgCl, so we put the 1 mole of AgCl on the top. Then finally, we want to convert to grams of AgCl. So we'd look up Ag on the periodic table, Cl on the periodic table, add them together, and what we find is for every 1 mole of AgCl, which we want on the bottom so it'll cancel out, it has a mass of 143.32 grams of AgCl. Multiply by the top, divide by the bottom, repeat to the end, and we find that this should yield 1.31 grams of AgCl. So I hope you found this helpful. Again, this relatively short video, I know is a little longer than I wanted it to be, but this relatively short video does not replace a couple weeks worth of lectures. If you would like more practice with this, please do see the video description where we have a mini course set up for you where you can practice this stuff online, since you're probably already past it in your lecture course. I'm now going to turn it over to Tim, and he's going to go over the pre-lab that you need to do before you come to lab.
Hi everyone. So, like Colin said, I'm going to go over the pre-lab portion of this experiment now. So, in your lab manual, you have a pre-lab, which you're supposed to do as practice before you come to lab during your regularly scheduled lab this week. Once you get to lab, you're going to do some more problems with your class before you have to fill out a problem set individually. But for now, I'm going to go over this pre-lab so that you are able to have this completed before you come into lab during your normal lab period. So, the first thing we're going to do is we're going to do some mole to gram conversions. Well, our first one is going to be how many moles of H3PO4, which is phosphoric acid, are in 94.052 grams of H3PO4. Well, anytime we want to convert from grams to moles, which is what we want to do here, we're trying to go from grams of H3PO4 to moles of H3PO4. Anytime we want to go from grams to moles, we need a molar mass. So we're going to have to figure out the molar mass of H3PO4. Well, if we look at our periodic table and we do 3 H's plus 1 P plus 4 oxygens, so that's 16 times 4 plus 30.97 plus 3 times 1.01, we find that the molar mass of H3PO4 is 97.994 grams. So that many grams of H3PO4 is equal to 1 mole of H3PO4. So now we can convert from grams to moles. So we start with what we're given, which is 94.052 grams of H3PO4, and we want to convert it to moles. So if we want to convert it to moles, we want the grams to cancel out, so we want to put the grams in the bottom. Well, we know that we need to put 97.994 grams of H3PO4 on the bottom, and on the top, that's equal to 1 mole of H3PO4. So now we have our conversion from grams canceling out and leaving moles, so we're going from grams to moles just like we want. So if we multiply by the top and divide by the bottom, or in this case just divide by the bottom because the top is multiplying by 1, which doesn't do anything, we find that we have 0.95977 moles of H3PO4. And it's important that you do make sure you have the right number of significant figures. We started with 5, we did multiplication and division, so we need to end with 5 significant figures. So we've converted from grams to moles. Now we're going to do the opposite. We're going to convert from moles to grams. In this case, we're going to do it with AgNO3. So just like before, to convert from grams to moles, we needed a molar mass. Well, to convert from moles to grams, we also need a molar mass. So if we go back to our trusty periodic table, we need 1 Ag, we need 1 N, and we need 3 O's. So 16 times 3 plus 14.01 plus 107.87. And we find that for AgNO3, 1 mole of AgNO3 is equal to 169.87 grams of AgNO3. So now we have our conversion factor and we can convert from moles to grams. So we start with our 2.76 moles of AgNO3. And we want to convert that to grams. So we want the moles to cancel out, so we're going to put the moles on the bottom. So we put 1 mole of AgNO3 on the bottom. And in the top, we put 169.87 grams of AgNO3. Now we multiply by the top and divide by the bottom, or in this case just multiply by the top because dividing by 1 doesn't do anything. We find that we have 469 grams of AgNO3. Said another way, in 2.76 moles of AgNO3 there are 469 grams of AgNO3. So now we've gone from grams to moles and moles to grams, and in both cases we used the molar mass of the material we were talking about in order to make that conversion, because anytime you want to go from grams to moles or moles to grams, you need a molar mass. And I realize that between Colin and me we've said that a lot during this video, but that's just because it's really important. The conversion from moles to grams and grams to moles is central to what you're going to be doing for pretty much the rest of your time taking chemistry. So it's really important that you understand how to do that. Next, we're going to take something that's a little bit of a detour. So we're trying to do some balancing chemical equations. Well, why is that important? Well, if you remember from earlier in the video, when Colin was talking about doing some stoichiometric conversions, whenever you were trying to convert from moles of one thing to moles of another, you needed a balanced chemical equation. So we think that this is a good time to get some practice balancing a chemical equation. Now, in this case, we have Al2O3 plus H2SO4 yielding Al2SO43 and H2O. Whenever we're balancing a chemical equation, it's always important to try to balance our polyatomic ions as polyatomic ions. So, said another way, we could try to balance the oxygens here, where we have 7 on one side and 13 on the other. We could try to balance them as oxygen, but it's going to be much easier for us if we balance the SO4 as SO4 and the oxygen as oxygen. So that's just kind of a trick we use to make our lives way easier when we're balancing these equations. Whenever I'm balancing these equations, I like to start with my polyatomic ions because normally they're the easiest to keep track of. So on the right side of my equation, I have SO43, so I have 3 SO4s. On the left side of my equation, I have 1 SO4. So in order to get 3 SO4s, I need to put a 3 in front of my H2SO4. So now I have 3 SO4s here and 3 SO4s here. Next, I like to check my metals and things like that. Personally, I prefer to leave my hydrogens and oxygens until the end because usually they're the easiest to just clean up with at the end. And if I check that, my aluminums, I have 2 aluminums on this side and 2 aluminums on this side. So for now, those look like they're okay. Keep in mind that if we do put a number in front of either of those, we would have to come back and check that they're still balanced. But for now, we don't need to do that. So, next we'll check on our hydrogens. On this side we have 6 hydrogens, and on this side we only have 2. Well, in order to get our 2 to become 6, we need to have a 3. So now we have 6 hydrogens and 6 hydrogens. The last thing we need to check, because we didn't change our aluminums there, is our oxygens. Well, on the left side we have 3 oxygens, and on the right, thanks to our new 3, we also have 3 oxygens. So this is a balanced chemical equation. Now we're going to move on to the second equation here. This equation is reacting C3H8 plus O2 to yield carbon dioxide, CO2, and water, H2O. Any reaction that follows this form is called a combustion reaction. It's important to remember what your types of reactions are. The first one we did is kind of a strange one, but this bottom one here is a very clear example of a combustion reaction. So what we need to do is we need to balance our combustion reactions. And anytime we want to balance combustion reactions, my advice to you is save your oxygen for last. The reason we save oxygen for last is because it's the only thing that's by itself, so it's usually easiest just to add whatever we need to here in order to fix it. It's much easier to start with our C's and our H's because they only appear in one spot but never by themselves. So I prefer to start with either my C or my H and then come to my O later. So for this example, let's start with our C's. On the left side we have C3, so we have 3 C's, and on the right side we just have 1 C. So in order to have 3 carbons on both sides of this reaction, we need to put a 3 in front of our CO2. Now, we want to do our hydrogens, because remember I said we want to save our oxygens until the end. On the left side of the equation, we have 8 hydrogens, and on the right side we have 2. So in order to make this 2 into 8, we need to add a 4. Now that we've balanced our carbons and our hydrogens, we're forced to go to our oxygens last. So on the left side of the equation, we have only 2 oxygens. On the right side, we have 3 times 2 is 6, plus 4 is 10 oxygens. So we have 10 oxygens on the right side and only 2 on the left side. Well, to get 2 to become 10, we need to multiply by 5. Now we have 3 carbons, 8 hydrogens, and 10 oxygens on both sides of the equation. So we have our balanced chemical equation. Remember, the reason we're doing this is because if we were asked to do any stoichiometry involving the products and reactants in one of these equations, in order to convert from moles to moles, we would need these stoichiometric coefficients. It's also important to notice that any blanks or spots where there's no number written, there is an implied 1. We just don't write it down because that would unnecessarily crowd our reactions. So now we're able to work on our stoichiometric equalities that are going to relate moles of one thing to moles of another. So it says that using the balanced chemical equations, we're going to use unit analysis or dimensional analysis to complete each problem, and it wants us to show all of our work. So our first reaction is 2 aluminums, solid, plus 6 HCl, hydrochloric acid, aqueous, yields 2 AlCl3, aluminum chloride, aqueous, plus 3 H2, hydrogen gas. So it's going to ask us some questions that relate to this chemical equation. Our first question is how many moles of hydrogen gas can be produced from 4 moles of aluminum? Well, if our question is asking us going from moles of aluminum to moles of hydrogen gas, we're going to go from moles of aluminum to moles of hydrogen gas. Well, anytime we want to go from moles of one thing to moles of another, we're going to need to use our balanced chemical equation. So luckily it was given to us, we didn't have to solve it, and we can use it to solve this problem. So we start with 4 moles of aluminum. Next, we need to convert to moles of hydrogen. To do that, we're going to use the stoichiometric coefficients for aluminum and hydrogen in this problem. We want moles of aluminum to cancel out, so that's going to go on the bottom. So in our balanced chemical equation, there's a 2 in front of the aluminum, so that means for every 2 moles of aluminum, we have, for hydrogen, a 3, so that means we have 3 moles of hydrogen. So for every 2 moles of aluminum, we have 3 moles of hydrogen. So we multiply by the top and divide by the bottom. In this case, we actually have to do both because neither of them is a 1. And we find that for every 4 moles of aluminum, we can produce 6 moles of hydrogen. So said another way, every 6 moles of hydrogen that we produce, we need to use 4 moles of aluminum. This is important stuff to know for when you're performing a chemical reaction in a lab, and you need to know how much of your reactants you need in order to produce the amount of product that you want. So, let's do another problem using the same equation. In this case, we want to know how many moles of hydrochloric acid, HCl, is required to use up 3.5 moles of aluminum. Well, again, we're going from moles to moles. This time we're going from moles of aluminum to moles of HCl. Now, this might feel weird to you because aluminum and HCl are both reactants. But that doesn't really matter when we're doing stoichiometry. We can convert, like Colin did with hydrogen and oxygen forming water, from reactant to reactant, reactant to product, product to product, or product to reactant. We can go any which way we want between any two chemicals in our balanced chemical equation. In this case, however, we are doing 3.5 moles of aluminum, and we're going to convert that to moles of hydrochloric acid. Well, to do that, we need our balanced chemical equation. We need our stoichiometric coefficients. So for aluminum, again, we have 2Al, so 2 moles of aluminum. For HCl, we have a 6 in front of it, so that means that we have 6 moles of HCl. So we multiply by the top and we divide by the bottom, and we get 10.5 moles of HCl, which we need to round to 11 moles of HCl due to sig figs. Because we started with 2 sig figs and we're doing multiplication and division, so we end with 2 sig figs. So, for our last problem using this equation, how many moles of hydrochloric acid must be consumed in order to produce 0.15 moles of aluminum chloride? Again, it seems like there's something fancy going on here because we're talking about consuming chemicals, but in the end we're just talking about moles of one thing and moles of another. So in this case, we have moles of aluminum chloride, moles of AlCl3, and we're trying to convert to moles of hydrochloric acid, moles of HCl. So we start with our given here, our 0.15 moles of AlCl3, and we're going to convert it to moles of HCl. To do that, we need our stoichiometric coefficients. For AlCl3, it's a 2, so on the bottom we're going to put 2 moles of AlCl3, and we're converting to hydrochloric acid again, so we want the stoichiometric coefficient in front of HCl, which is still 6 moles of HCl. We multiply by the top, we divide by the bottom, and we find that every 0.15 moles of AlCl3 we want to produce requires us to use 0.45 moles of HCl. So in a lab, if we knew we needed a certain amount of a product like aluminum chloride, we know, thanks to this stoichiometry, that we would have to use at least 0.45 moles of HCl in our reaction in order to get the amount of product we wanted. It's really important to know that when you're doing science, because if I used too little, I couldn't make all of the aluminum chloride I need, and I need to redo my reaction in order to make that happen. So, we have one more problem to do here. we have a solution stoichiometry problem, which, if you'll remember from before, relates our molarity unit into the equation. So in this case, it wants to know how many grams of NaHCO3, which is called sodium bicarbonate, are needed to make a 25 milliliters of 5.4 molar sodium bicarbonate, NaHCO3, it clarifies it here, solution. So we need to know what we're starting with, what we're going to convert to, and what we're going to end with. So in this case, we're starting with our 25 milliliters of solution. So again, like Colin said before, we can never use milliliters when we're doing the solution stoichiometry because molarity relates liters. So we're going to just start by dividing that by 1,000 to make it liters. But we're going to start with liters of sodium bicarbonate, NaHCO3. And we're going to convert that to moles of sodium bicarbonate. When we have liters, the only thing we can really convert it to is moles. We can't convert it directly to grams because we can't relate grams to liters without a density, which we don't have in this case. So we're going to go from liters to moles. So whenever we want to go from liters to moles, we have to use the molarity. Just like whenever we want to go from grams to moles, we have to have the molar mass. So we need to know that we need to go to moles of NaHCO3, and we have the molarity, so we'll be able to do that. Lastly, since we want grams in the problem, it says how many grams are needed, we will convert from moles of NaHCO3 to grams of NaHCO3. So, now we can start working on the problem. Well, we're going to start with liters of solution. We had 25 milliliters of the solution, so we're going to divide that number by 1,000, and we're going to start with 0.0250 liters of NaHCO3 solution. And we're going to convert that to moles of NaHCO3. Remember, 5.4 molarity means that 5.4 moles per liter. Said another way, 5.4 moles is equal to 1 liter of solution. So we have an equality we can use to convert from liters to moles. We want the liters to cancel out, so we're going to put the liters in the bottom. So on the bottom we have our 1 liter of NaHCO3 solution, and on the top we have our 5.4 moles of NaHCO3. So now we've canceled out our liters and we've gone from liters to moles. Well, now we want to go from moles to grams. To go from moles to grams, like I said before, we need a molar mass. So we need to go back to our periodic table and we need to add up Na plus H plus C plus O3. So we need to multiply the 16 by 3, add 12.01, add 1.01, and add 22.99. When we do all of that, we find that the molar mass of NaHCO3, we find that 84.01 grams of NaHCO3 is equal to 1 mole of NaHCO3. Sorry for it being a little crowded there, but we find that 84.01 grams is the molar mass, so 84.01 grams of sodium bicarbonate is equal to 1 mole. So we want the moles to cancel out, so we're going to put 1 mole on the bottom. And on the top, we're going to put our molar mass, which is 84.01 grams of NaHCO3. Now we're going to multiply by the top, divide by the bottom, multiply by the top, divide by the bottom. In this case, the division is silly because they're both 1s, so we're really just going to multiply by the tops, and we get a final answer of 11.3 grams of NaHCO3. So that means that in order to make a 0.0250 liter solution of sodium bicarbonate at 5.4 molar, we need 11.3 grams of sodium bicarbonate. Said another way, if we took 11.3 grams of sodium bicarbonate and divided it in 0.025 liters, 25 milliliters, our solution would have a molarity of 5.4. So, now we've gone through a few different types of problems that you'll see in class and in your lecture and on your tests in order to give you an idea of how to do the various types of stoichiometry. It's really important that you practice these. Practicing them is the only way to get better. This is the same thing as basketball or playing an instrument or anything else on earth. To get better at it, you have to practice. So it's really important to practice these as much as you can. Like Colin said before, if you look in the description of this video, there is a mini lecture in which Colin will go over further how to do these problems and how to learn the material. So, thank you for your time, and good luck in lab when you show up to do your stoichiometry experiment.